Hi everyone, this is a video I've had about 5 or 6 different goes at it to try and get it all in and correct and everything else, and today I might have a bit of free time, so we might be able to finally get it complete. This is sort of a continue on from everything else that we've done in the past, asymmetrical regauging experiment, all that sort of thing. This is a sort of a continue on from that, and we're going to just recover some of that stuff. Basically, for the simple reason is we had a long time that we were down, and it sort of really did interrupt our momentum quite some amount. Anyway, you can see this is a thread that I started a little while back, parallel wire or bifilar coil experiment. We've only got 6K views at the moment. Not a lot of people sort of really took a lot of notice of this. There was no one that I know that sort of really took any experiment any further on this thread, which is a bit of a shame. To be perfectly honest, this was the precursor to learning what we've learnt so far. Anyway, we covered quite a bit of stuff in this thread. The thread itself, obviously the meaning of the thread, the title of the thread, parallel wire or bifilar coil experiment, is trying to get everybody to think along the lines of what's going to happen with current flows in a parallel wire or a bifilar coil. Now, the term bifilar has been used a lot, and its meaning has very, very poor definition in most circles. The reason being is a lot of people call two separate coils on a transformer or something along those lines bifilar coils, and they're not. The definition of bifilar is a parallel wire running the entire length of the wire side by side. Okay, it's got to be parallel, the entire length of the wire side by side, wound on a former. And down this thread a little bit, you'll see in a second, I actually show a transformer that has been wound with a bifilar coil, and that's exactly what the coil is. It's two wires wound parallel side by side for the entire length of the coil. I think at this stage this is going to be the first video in a series of videos, and the reason being is I just don't think we're going to fit everything in these videos. And I want to tell you straight up, I am not going to discuss measurements. Okay, if you want to go through and put measurements down and all that sort of thing, then great. I urge people to do that if that's what they wish. This thread is not intended to prove above unity or anything like that. That's not what I'm about. What I'm about is to capture and observe effects and make those effects do useful work for us. Okay, I am not here to have a competition over who can read the scope the best or anything pathetically silly like that. I know my way around a scope pretty well. Anyone that would like to challenge me, I'm basically not interested. I honestly am not interested. Okay, if that's the way that people think, then I don't have time for that sort of silly childish carry-on. So I'm not here to discuss measurements. What I'm here to discuss and here to observe and here to learn is the effects in these machines. And if you think you can see something that might put out 50 times more energy than what we put in, then great, but I'm not going to discuss that. That's not what I'm here for. It's not what I'm interested in. And I've said all along, look for the effects. I've said look for the effects for that very reason, because people will often do one experiment. They will check the figures on it. The figures will be, maybe 80-90%, something like that. And then they give up. That's it, they give up. So I don't like to give people false hope, because I know that a lot of people just won't carry on. So look for the effects. If you're looking for effects, then it makes the path of investigation so much more fun, so much more exciting, so much more of an experience that you can enjoy rather than get frustrated after 5 minutes of work. Like I said, once you understand these machines, once you understand what's going on, and once you know what to aim for, then building these machines is extremely easy, very, very easy. But you can't just jump in on the first experiment and expect to succeed. You just can't do that. It's not how this works, and I don't know why. I mean, you can build a tank circuit, you can predict it, you can do the whole lot, and it goes. These machines are different. I don't know why. I know they work. I know there's a lot to it. I know there's another half of science to these machines. I still can't predict a machine. I've still got to sit down and work at it until I get it working. I'm getting much better at it now. The first time I sat down and messed around with this sort of thing, it took me a long time to understand it and a long time to make it something that was, it's hard to describe. It's sort of like a new technology, so you're sort of following a path that really has no direction, so sometimes you sort of end up down rabbit holes. Anyway, parallel wire or bifilar coil experiment. This was sort of the precursor to me doing the asymmetrical regauging experiment. I really sort of wanted people to understand certain things before we tackled the asymmetrical regauging experiment, which we're going to look at a little bit more in the later in this video or in the next video. So worth going to have a read. This is a transformer. I've got quite a lot of these transformers. It's out of a UPS. Red obviously is the 24 volt positive. Obviously the white and the black there are switched. That's the MOSFET side, so it's a half bridge if you like. And you can see here, there's one wire there, and they come up into the same terminal. So this transformer is a parallel wire or bifilar wound transformer by the very definition. Now what I wanted people to think about, and people don't seem to really take the time to think about it unless they're encouraged to, what I wanted people to think about was this. Okay, the normal flow of current in a parallel wire exposed to a modulating magnetic field and connected to a load. Okay, in the parallel wire we would have current that flows in both the same directions. Okay, what I wanted people to think about, the goal, this must be brought about at the right time. Remember, this is how current is amplified. Now, in this experiment, we didn't really sort of take this further because the next stage was asymmetrical regauging experiment, but I wanted people to think about this beforehand. So if we can get the current moving this way in the black wire, but in the red wire moving this way, then the magnetic fields cancel. Okay, now superposition. So if we were to say 1 Gauss plus -1 Gauss, we get a zero net force, or zero net Gauss produced from this wire. Now, we've just recently had a discussion with a couple of people on our backup forum, and the basic analogy to Lenz's law, and this is actually incorrect. Okay, so let me just state that first. Lenz's law, people often think of Lenz's law as the force that needs to be overcome. Okay, the force of magnetic field or whatever that gives a rotor on a generator drag or torque, which is not the case. Okay, Lenz's law predicts the negative voltage in the Faraday's law equation. Okay, it doesn't predict current, doesn't give you anything to do with current. It's not current at all. current is the mmf. Okay, mmf is the current through turns, which is ampere turns. Okay, so ampere turns is the equivalent to mmf, magnetic force. Now, magnetic force is the magnetic field, and if the magnetic field changes in time, then it's a source of energy. Okay, so anytime we have a current in a wire, there's always going to be a magnetic field around that wire. Okay, so Lenz's law, everybody has always said in the past, and this is well known through all the circles out there, if you can beat Lenz's law, you can get, you know, above unity. You can beat the unity boundary, and it's true, you can in some situations, not all the time. Now, Lenz's law is critical. The force of mmf, a different thing, is also critical. Now, if you don't have the force of mmf in this wire, then you don't have any current. Okay, it's as simple as that. To have current, you must have an mmf, a magnetic force. Maybe if we go back to our transformer, okay, our input is on these wires on the back here. Okay, so our input coil might be roughly on this transformer, might be around about the 400 turns. It might be something like about a 0.8 millimeter wire. 400 turns. It's going to have a fairly decent impedance. Okay, so when the input is on, there's a current that flows through the input coil. Okay, so that current is entirely dependent on, first of all, the impedance of the input coil, and then the load conditions on the output coil. Okay, if we load the output coil, then a current will flow in these parallel wires on the transformer. In this situation, it'll flow in the same direction. Now, this current that flows is directly opposing the current that flows on the input. Okay, so as the secondary coil is loaded more and more, then the input current will go up more and more. And what's happening in there is the magnetic fields are interacting together, which lowers the impedance of the coils. As the impedance of the coils go down, then the current goes up. Okay, so basically it's a Ohm's law type sort of scenario. Now, if you have one, let's say one magnetic force, which would be one, let's say Newton per kilogram. So magnetic force of 1 Newton per kilogram, which, let's say, just for messing around purposes, that we've got 1 ampere through 400 turns. So that means we've got 400 ampere turns on the primary coil. Now, if we've got 4 turns, let's say, we haven't, but let's say we had 4 turns on the secondary coil, then we'd have 400 amperes. Sorry, 100 amperes. 4 times 4 is 400. So in an ideal transformer, what I'm trying to say is the ampere turns on the primary coil would be equal but opposite to the ampere turns on the secondary coil. So we're talking ideal transformer, lossless. We're not considering losses at this stage. So in a lossless transformer, the ampere turns, or the magnetic force on the input, is the same as what the output is. Okay. Now, how do we get around that? Okay, that situation is not Lenz's law. Okay, that situation gives us torque on the generator shaft. That situation gives us a magnetic force in the transformer, which is not Lenz's law. Okay, this is something that people have overlooked and confused and not understood properly for forever, basically. I'm sure the greats back in the day knew what the differences were, and perhaps it's been written out of the textbooks or whatever, who knows, I don't know, but it's not Lenz's law. it is magnemotive force. It is the magnetic field. Okay. There's a big difference. Okay, Lenz's law, again, it predicts the negative voltage. So if we have a magnetic field, a north pole moving in at a rate of change over time, okay, now if that happens, then the voltage generated by that magnetic field will be the opposite. Okay, so it's negative. The sign is negative, which means it's opposite. Okay, it's not magnemotive force. Magnemotive force is the current through turns. So it's important to understand. This is something that so many people get wrong all the time. It's just people just don't understand it. Yet at the same time, this is extremely simple to prove on the bench. Okay, you can generate a voltage in a coil and have no magnetic field. The current doesn't flow. Okay, easy to measure. The voltage is there, but no magnetic field. There's no current. As soon as you load the coil, then the current flows. Then you have a magnetic field. As soon as you have a magnetic field, you have current through turns, ampere turns, current through turns, and then a magnetic field is produced in the coil, and then that magnetic field produces the torque, if you like, or the restrictive forces. It's a drag force. Now, believe it or not, this is just a useless bit of trivia. In a transformer, there's really no word in the English language that properly describes what's actually going on. And I believe that's just absolutely crazy. The closest word that I've found, which is really not ideal, is compression. A magnetic compression. Okay, so if the magnetic field on the primary is equal but opposite to the magnetic field on the secondary, there's a magnetic field compression going on. There's really no word to really describe it properly. There's no word with a definition, a proper definition. I mean, there's all sorts of talk of torsion fields and tension, you know, tension on the wires and all that sort of thing, but the actual definitions of those words don't fit, technically don't fit what's actually going on in the transformer. So the true and correct situation is a magnetic field compression, but there's more to it than that. Magnetic field compression doesn't really describe what's going on properly. Anyway, I see we're up to 18 minutes already. Now, study the transformer, study the generator, okay? Because these machines that we're working on, the next step ahead from a transformer and from a generator, okay? Magnetic compression is what's going on between the coils, between partnered output coils, partnered output coil 1, partnered output coil 2. There is the same magnetic compression going on, okay? Now, without that compression, back to what we were talking about before, without that compression, if we had no compression or redirected one of the compressions into maybe another circuit, okay? So if we're able to redirect the magnetic field on the secondary coil into another circuit, without the compression that I've just explained, there can be no current flow. Okay, essentially that coil then moves into an off state, okay, and essentially the current would stop flowing almost instantly. The voltage would drop to zero. Okay, so to keep a current flow, and I've shown this in my series already, and you can go back and watch that. I believe it was either video 6 or video 4, I think, from memory. One of the two anyway, but go back and you can watch it. Now, without the magnetic field compression, the current stops flowing instantly. Okay, it's like you've switched the coil off. So if you want a current to flow, then you've got to keep the compression of magnetic fields as high as you can, which means you have to hold the voltage as high as you can, but you need a second source, okay, to do this. So if we were to redirect the magnetic field on the secondary coil only, or to put this another way, if we had a a pulse put into this transformer which brought the terminal voltage on this coil up as high as possible, and then instantly, as soon as we got to maximum voltage, we switched in a load into this coil. Okay, and then at that stage the input coil would be off, so the input coil over here would be off, and then we switched into a load into the secondary coil, and the current would flow, but it would drop down very, very fast. Okay, you'd see a time weighted average of almost an exponential decay of voltage over time. And the reason for that is there's nothing supporting it. So gravity, if you like, would be bringing the voltage potential down. The current would obviously reduce as a result, and the coil would lose its magnetic field. And that can be timed. I believe I did go through a little while back. I believe there's something to do with gravity, which is 9.84 or something, so you can actually calculate it. Anyway, so if you want to extend that period of work where the magnetic field is actually going to be opposed, if you like, if you want to extend that, then switching in a load at peak voltage on this coil would be ideal, but also switching in a load on this coil over here would be even better again. Okay, so you're doing both coils essentially, and then the reason for that is basically each magnetic field opposing in this coil would pump electrons from the source, from the atom. Okay, the copper atom has 29 electrons, so each electron and each atom, especially in the outer orbitals, would be put under a bit extra force, and the outer orbital electrons would be forced to move down the wire. Remember, electrons carry a charge, carry a magnetic field. Obviously an external magnetic field can make them move. So there's a lot to it. I've said before, there's a lot about electromagnetic induction that is missing. It's incomplete, and I believe to a certain degree that we have completed it. AboveUnity.com members have worked hard to try and complete most of it, but there's still some that's not 100% known. Okay, so it's really funny, because once you get to a certain stage you think, wow, how far can science be behind? That's just such a joke. It's just unbelievable. This is really simple stuff, and science is just not there with it. It's so easily provable on the bench, yet science just doesn't even, there's not even a single calculation, a single prediction, a single mention of current in Faraday's law, which I find a little bit amazing, because there's so many variants of coil configurations that you can use to actually do different things, you know, and Faraday's law just doesn't cover it all by itself. And yes, you can apply Ampere's law and all those other laws as well, you know, Lorentz force law, all that sort of thing, you know, but still doesn't always give you what you want. There's still a lot missing. Okay, so what we're going to do now is, I've given you a bit of background. So our thread on parallel wire bifilar coil, we went through and we basically gave this analogy. Okay, so typically in a conventional transformer you would have current in a parallel wire, you would have current going the same way. Okay, so ends tied out to a load, current would go the same way. So to get around Lenz's law, okay, to make sure that your magnetic fields are not exerting a force on the primary coil, okay, all you need to do is you cancel your secondary coil magnetic fields. Okay, superposition. So if we were to say ampere turns of the primary coil was 1, ampere turns of this black coil here was 1, ampere turns of this red coil here was 1, then we'd have 1 plus -1 plus 1, which equals 1. Okay, now I did actually go through and I did actually show that on the first post on the asymmetrical regauging experiment. Okay, so here we go. Chris's non-inductive coil experiment, asymmetrical regauging, it basically is, that's what it is. Anyway, so this is Andrei Melenchenko around about the year 2000. I think this document was released, and all I've done is just copied this image and put it up on the site. So H1 plus H2 plus H3 equals H3. So you have H3 left over, okay? And it's because of the configuration of the coils, okay? You have magnetic fields that are interacting, which give you a total result of the H3 magnetic field in this case. I'm not sure why Andrei Melenchenko didn't use magnemotive force. I mean, H is essentially, it's the field strength of the coil. But anyway, it doesn't really matter. Everybody's got their different ways of doing things. So in a symmetrical transformer with 2 wires, okay, so H1 plus H2 would equal 0. So what Andrei Melenchenko is showing here is exactly what I've just explained. H1 plus H2 plus H3 equals H3. So instead of cancelling the component on a symmetrical conventional transformer, instead of cancelling the H component, we're left with a H component that's left over. Okay, so we end up with more work done in the system, and that's really what it's about. It's about net force or work done in the system that exceeds the work that you put into the system to get it to do what it's about. And once you've done that, then it's above unity. So everybody watching this video, I ask, go through, read this thread, read all the other threads prior to this, the parallel wire bifilar coil experiment. This thread here, go through and replicate this machine if you haven't already. It's worth doing. Don't just do it once and then give up on it. You're going to have to spend a little bit of time on it and think about it, because if you're going to do it once and really just put it behind and say, oh, it doesn't really work, then it won't work. There is a little bit to it. You've got to try and understand it, and basically the understanding to this machine, once you understand it, is so simple it's just not funny. Once you understand it, you're going to think to yourself, how did I not figure this out before? This is so simple. And it is. It's about the force on the wire. Okay, so force on the wire, you want to increase the work done in the machine, and that's the third force. So this is asymmetrical. We're moving from a symmetrical conventional transformer. Like I said before, we're just extending the conventional science just a little bit, not much, just a little bit. We're just adding asymmetry to Faraday's law, okay, and to Ampere's law and a few other laws. So by adding asymmetry, you can quite easily achieve results that you would normally not see on the bench at all. Okay, and this is the important thing. This is something that people just don't seem to quite grasp initially, is what you see on the bench. If you monitor your currents, okay, if you watch what's going on properly, you'll see things, the effects, okay, remember what I said, look for the effects. You'll see effects that you just do not normally see on the bench, effects that conventional science currently can't explain. Okay, so this is really, really important stuff. If you want to learn, it's a journey to learn and build these machines. Once you learnt the basics, then the rest is pretty straightforward, pretty easy. Okay, a little bit of messing around to get a machine working, but the rest is pretty straightforward, pretty easy. So we're going to move over to the bench now. That's probably enough rambling just at this stage. Again, the time that we were down has really sort of thrown this a little bit back. I was hoping to release this quite some time back. So this is the thread, Chris's electromagnetic charge pump experiment, and that's exactly what it is. Okay, you've got a piece of copper that has copper atoms insulated in a long cylindrical, some people call it a wire, and all you're doing is you're forcing that electron that's attached to the outer orbital, you're forcing that electron down the wire with a velocity. So you're increasing or you're accelerating the electrons in the wire. Very, very simple, very straightforward. Now I've let a few people actually have a look at this thread. This was posted September the 25th. No, it wasn't, sorry. This was posted 11th of November 2020. So we're quite a ways behind target at the moment. I was hoping to get this up and get it posted and get it out so that others could start using this information. Now this is the thing, okay, this is the thing here, and I say this for a reason. You know, some have spent 50 years searching and we've found what they couldn't find. Some have degrees, BAs, PhDs, all sorts of education under the belt. Education doesn't mean, by any means, smart. Sometimes you've got to explore territory that you're not familiar with, and by exploring territory that you're not familiar with, it's an adventure. And some people are just not willing at all to adventure out of their comfort bounds. Okay, if they can't read it in a book, as far as they're concerned, it doesn't exist, and that's really sad. When science is that shallow and that unscientific, then humanity has a real problem. So it's really, really sad that things have gotten the way that they are. Anyway, we're going to head over to the bench. I just wanted to show you that, give you a bit of background. Those people that are into this fresh, again, please do not start here. Please go back, please replicate those other threads and everything, and then move on to this next. Otherwise this is really going to be difficult. This is really going to be hard to grasp. Some of it I will cover again, but you really need to know the basics. You really need to know the simple things that really give you a leg up to get to here first. Okay, now most of you will know already, we already have a thread builder's guide to above Unity machines. Go follow that. There's tons of information there, all the answers to get you up to where you are or where you need to be before you start this. This is probably far too advanced for most people. Most people just will not understand it.
Okay, hey guys, we're on the bench. So this is the wire that I was trying to show you. So the goal to get the currents going the opposite direction. So I've wound it on a small, well, it's not small, but I've wound it on a former. You've given it a little bit of a clean up, bit of a tidy up, tin the ends, and what we're going to do is we're going to give it a little bit of a go and see if we can get the current to go in the opposite direction. Now remember, the goal is to get it going the opposite direction for the very, very simple reason is it's superposition. And obviously with superposition, if we can get the magnetic fields in the output coil to cancel, at least to a certain degree, then obviously the input is not affected so much, negatively at least anyway, by the secondary coil. Obviously in a conventional transformer, again, you know, the magnetic force, so as you load the output more and more, the input goes up and up. So we want to change the situation. We want to make a machine work that we can load as much as we can, and most of us have done it. Most of us already know how to do this, so I'm just sort of taking that step further now.
Okay, so what we're going to do is we're actually going to apply this to our transformer, which we actually showed in the thread. So this center here, or center tap if you want to call it a center tap, was the red wire, I believe the black wire and the white wire, which I've cut off. I've taken the insulation off. We've got the 3 wires at the back. They're the input wires. Now this is a 220 volt 240 volt transformer. It was from a 1500 VA volt ampere UPS, so obviously 24 volts was switched like that at 50 Hertz. Australia runs at 50 Hertz, so we're going to apply the same idea that I've shown here. We're going to apply that to the transformer. Basically it's easier. We can run with the parallel wire. You can see, let me try and focus it a bit. There you go. You can see we've got the parallel wires there, so it's bifilar. It's a slightly different color than the other one that I've got, that I've shown, but the idea will be exactly the same. So the goal is to use 2 wires and to run the currents in each wire in opposite directions. So you remember, typically current will flow one way in a parallel wire. There we go. So it'll flow one way, parallel wire or bifilar wire. We want it to flow into opposite ways. So let's finish that off now. I just wanted to show you at this stage that that's what we've got. So I'll cut the wires and we'll configure it so that the magnetic fields are set up so that there's superposition going on, at least to the best of our ability. And remember, there is a coupling issue, so sometimes we can get into these transformers and sometimes have coupling issues, but if there is, then we'll deal with it then. Okay, we're back in a minute. Alright guys, so what we've done here is this outlet, or this terminal, these terminals, plural, are the outlet from the bifilar or parallel wire over here. Two diodes, one back to back, okay, or one in, one out. Essentially this is going to be a half wave rectification. So what we're going to do is we're going to monitor the currents on each wire. You remember I said monitor your currents all along. Okay, so in here and then out on this wire, out here, and then in on this wire. Conventional current, we know it's the other way, but anyway, so we're going to use 2 measurement blocks. We're going to use these globes as a load. Okay, so they'll be banging the end of there. We're going to get it up and running, and we're going to have a look at the currents. Guys, so this is the setup. It's pretty straightforward, and just through to the scope. We've got 4 channels set up at the moment, but only 2 switched on. Channel 1, channel 3 are the currents. So we're measuring the currents via the measurement blocks here and here. And in a minute we'll have a look at the voltage on one of the channels at least anyway, if not both, and see what we can find as well. So just to quickly reiterate, what we're looking for is we're looking for the change in current in one of these wires producing the opposite effect in the other wire. Okay, so Faraday's law, essentially the changing current, which is essentially the magnetic force in one of these wires as it's loaded, as this diode conducts, should create a voltage in the opposite direction on the other coil. Voltage through a resistive load should then allow for current flow, and the current flow should give us a difference in potential between the 2 different wires, bringing about current flow in the opposite direction, at least according to
Faraday's law and how we understand it currently.
The system's on. What we're looking at is our setup with an AC or a sinusoidal waveform into the transformer via the plug here, into our input, obviously diodes we've covered, out through our measurement blocks, two lights, so two loads. Now again, I just wanted to cover before, what we were looking for was the change in the current of one of the bifilar coils producing a voltage in the other. Okay, so technically the coupling should be better between the bifilar coils than from the input coil to the two bifilar coils. It gets technical, I know. Now I just want to say, every time I hear the term bifilar, I always try to think of a bifilar coil as two separate coils. That's how I think of it, and that's how I reference it. So when I'm talking about the coils, please understand that that's what I mean by bifilar. Now initially, looking at the scope, it looks like a failed experiment. It looks like we have nothing there. We've got 0 on the gradical line. There's a little bit of what some people might deem as noise down the bottom. So just on the blue, which is the voltage, yellow current, pink current. So the blue there does show a little bit of what some people might call noise on the 0 gradical there. However, if we turn the voltage down at 5 volts, we get a dip. So as the current is moving up here, we do get a dip down here. So the blue and the pink are the same coil. Okay, so the blue gives us a little bit of voltage just in there. Alright, so this experiment is, some people would call it a failed experiment, but on closer investigation there is something there. There is, Faraday's law is occurring between the coils, and we do have a voltage which is generated, okay, EMF is generated by the change in this current up here. However, in saying that, there is an issue where it very quickly drops off and falls back to 0. Okay, now there's lots of things that could be causing that. It could be just the coupling of the coils. So initially the coupling is weak between the primary and the secondary, and then the tertiary, and then after that it dips off. Okay, other things could be causing it as well. To be perfectly honest, it's a little bit of a complex area, and I'm not really quite sure exactly what is restricting, why it's so restrictive in this area. The fact that the primary has a lot more magnemotive force, obviously because of the turns, than the tertiary coil in this situation, at least anyway, could be playing a role as well. Okay, it's a very closely coupled transformer, so we could be seeing issues with that particular coupling. So all in all, there is something there. People have overlooked this pretty much forever, and what we need to do is we need to actually start asking the question, what do we need to do to improve this particular effect? There's an effect here that currently is unexplored and unexplained by science. We have 3 interactions in a transformer, and you've seen already in that particular transformer there, it's not something that science explains or would like to admit. It's an effect that potentially we can investigate further to try and find out what's required to actually increase this effect and make it more prevalent and also worth our while in the long term. It's a technology that currently is not explained or completely ignored even.
A few thoughts. I think this is speculation, okay, so please understand that it's speculation. The transformer has some pretty unique characteristics. There really is no other machines like a transformer. The generator is the closest approximate analogy as far as I'm aware. So electromagnetic induction is a pretty unique sort of beast. Floyd Sweet said that in a transformer there's an electric field that surrounds it, a surging electric field that surrounds it. You can go and have a look at the quote if you like. So when magnetic fields cancel or oppose, or like I said before, if there's a compression of magnetic fields, and you've got to remember that there's two parts to this. So there's from zero to peak current, there's a compression, and then from peak current to zero again, this is on the sinusoidal wave, from peak current to zero again, then there's a sort of an uncompression, if you like. And like I said, there really is no decent words in the English language, at least that I know of, that properly explain these effects. These effects are largely unexplored and unknown to most of the scientific community. Only people on the bench that would be willing to sit down and do the experiments can actually see these effects. So we're sort of dealing with effects that, again, this is an avenue of adventure, exploration, that most people won't even look at. If it's not written in a textbook, most people won't even look at it. So we're on the verge. We're on the verge of a whole new science. The negative signs were written out of science by several different people, one of them being Richard Feynman, and he did actually admit to it, saying the negative sign was the greatest problem that science has ever faced. But in writing out that part of science has actually been forgotten. And there's some scientists these days that are actually looking at things like negative permeability and so on and so forth. So it's not entirely forgotten, and it's not entirely wiped. People are starting to realise that there's more to it. So I think the next step in this experiment is to use dioptics and actually to move on to a setup where we can separate the coils and we can actually monitor what's going on in the coils a little bit better. So a machine that you would have seen before